Hello and welcome back. This is Chapter 7, Video 3, in which we'll briefly explain the PDE system, which involves the QN equivalence rule. PDE equals SD plus SDE plus PD plus the QN rule. QN, for quantifier negation, is a replacement or equivalence rule which allows us to move the hook with respect to the quantifiers. If you look at what we've got here, we've got our equivalences expressed here, so you can make the substitution in any subpart of a formula. But if you have a hook outside of a universal, that's equivalent to moving that hook inside and changing the universal to an existential. Similarly, if you've got a hook outside of an existential, you can move that across inside the quantifier, and that quantifier changes to universal. So whenever you move a hook across a quantifier, it flips it to the other one. And if you think about this, and if you think back to the translations we did in earlier chapters, not all x are p is equivalent to some x are not p. And it's not the case that some x is p or no x's are p is equivalent to all x's are non-p. If you go back and look at the simple square of opposition in Chapter 5, you recall that we had diagonally opposite corners were contradictories. Well, if we take one of the corners and negate its diagonal opposite, we get equivalence, and that's what's happening here. Now, we don't actually need these rules. Adding QN is a conservative extension. There's nothing new that we can derive, but we can derive certain things much more simply. Let me illustrate with just a couple of examples. The full discussion is in the text. Typically, we would show equivalence by doing two derivations, one in each direction. I'll show two derivations that demonstrate the equivalence at the top end of this rule. To show the equivalence across the top, we need two derivations, one moving from left to right and one from right to left. Let's start with left to right. So we need to start with a negated universal claim. Not all x fx is of the form not all x p. So take that as our primary assumption. And our goal is to get some x not fx. Now, it turns out the easiest way to do this is by a hook elimination. So we'll assume the opposite of our ultimate goal. That is, we'll make the assumption of not some x, not fx, as an auxiliary assumption. We need to drive that assumption towards a contradiction, and the candidate for that contradiction is going to be line 1, which we will eventually reiterate at the bottom of the subderivation, and that would contradict all x fx if I'm able to generate it. Now, all x fx could come from fa by universal introduction as long as I can meet the requirements on the constant there in the universal introduction. Now, how can I get fa? Suppose I assume not fa as an auxiliary assumption for an interior hook elimination. That means I need to generate some sort of contradiction. Well, that's actually easy to do. With the not fa in 3, I can do an existential introduction, some x, not fx, 3 existential introduction. There are no restrictions there to worry about. And now I just reiterate line 2, not some x, not fx. And I've got a contradiction in lines 3 and 4, so I can exit the subderivation. Line 6 is going to be 3 through 5 hook elimination. And then the step to line 7 is going to be 6 universal introduction, where the constant a doesn't occur in any undischarged assumptions and doesn't occur in the final result in 7, so we meet the restrictions there. Then I just reiterate line 1, and I've got a contradiction in 7 and 8, so I exit that subderivation to the main scope line, and I cite 2 through 8 hook elimination. So clearly, some x not fx is derivable from not all x fx. What about the other direction? Well, let's reverse order here. So we take some x not fx as a primary, and we're trying to get not all x fx. Now, we have an existential in line 1, so we're going to need to start subderivation for existential elimination. And the ultimate goal of that existential elimination subderivation is the ultimate goal of the derivation overall. We want to try to work our way to this. And the assumption here has to be a substitution instance of line 1. So again, let's just use A. Now what do we do? Well, notice that our immediate subgoal here has a hook as the main operator. So a good thing to try would be a hook introduction. That is, assume all x fx as an inner subderivation and see if we can get a contradiction. And actually it's pretty easy to get a contradiction out of that. From 3, by universal elimination, we can get fa. That's one of our friendly rules, so we don't need to worry about restrictions. Now we just reiterate line 2 inside the innermost subderivation. 4 and 5 contradict each other, so we can add a hook to 3 while moving out one level. 3 through 5 hook introduction. Now we can move out to the main scope line by applying 1, 2 through 6 existential elimination. The constant we need to worry about here is A, and the 3 restrictions are that it doesn't occur in any undischarged assumption, which it doesn't because line 2 is being discharged as we do this. Its appearance in the innermost subderivation in 4 and 5 are irrelevant because those aren't assumptions. It can't appear in the original existential, line 1, which it doesn't, and it can't appear in our result, line 6 and 7, which it doesn't. So we meet all the restrictions. So we've just shown the interderivability of not all xp and some x not p, which justifies the equivalence replacement rule for the top row there. The book shows how to do it. These two as well. I'll leave it up to you. Now note that we don't actually need the equivalence or substitution rule here, but it does save a huge number of steps in any derivation. And if that negated universal or existential negation or negated existential or universal negation, if that was embedded inside a larger formula, it would be even more difficult to break out the appropriate piece and then apply these steps. So let's just see a couple of examples of how we would use this rule now that we have it. Here's a really quick derivation which takes advantage of the quantifier negation rules. Let's start out with this, not some x bx, as just a single primary assumption, and let our goal be not all x bx. Now, there's a couple different ways you can do this. You don't actually need the quantifier negation rule, but it's much easier if we use it. We could do it this way. Shove that hook in line 1 in, flipping the existential to universal. We get all x not bx. That's 1 QN. Now do a universal elimination on that, looking at not BA. That's a simple universal elimination. Now, if we've got not BA, we can do an existential introduction, get some x, not BX, and then do a quantifier negation where we pull that hook out across the existential, leaves the hook out here, changes the existential to a universal, and we wind up with that. Nice and simple. As another example, we could start with a basic existential like that and have as our goal, basically we're trying to show that we can go from some m's are g's to that's not the case that no m's are g's. In a way, this is moving from the lower left-hand corner of the categorical square to the negation of the upper right-hand corner of the categorical square. Let's see how it works. First off, what we're going to do is do a double negation on the primary assumption. So we'll get not some x, mx, and gx. That's just one double negation from SDE. Now let's take the innermost of those two hooks and move it across the existential. So now we have not all x, not mx, and gx. That's the quantifier negation move. Now we can do a De Morgan's on the interior portion of that formula. So we'll get not all x, that stays the same, not mx, or not gx. That's a simple De Morgan's. Distributing the hook across the conjunction, each side gets a hook and the wedge becomes a V. Now we can do an implication to change that disjunction into the conditional mx arrow not gx. And you may recognize that since we used equivalence rules all along here, we could reverse this derivation to show the equivalence of the primary assumption with the goal. We'll do one last quick derivation. It's not possible to fully illustrate all the things you might do with quantifier negation, but just give you a quick idea. Take these two primary assumptions. From these, all D's are B's and there are no B's, we should be able to get there are no D's. So let's put that in down here. Now you notice that the main connective of the goal is the negation, and you could do it by negation introduction, assuming some x dx, but then you'd have to deal with an existential elimination subderivation, and it would take quite a bit longer than what we will in fact do. First off, let's do universal elimination on line 1, and that'll get us dA arrow BA. Now let's do a quantifier negation on line 2. That moves the hook inside and gives us a universal claim to work with. That's one of the things that can be useful about the quantifier negation rule, is in some cases you'd rather deal with a quantifier than a hook, in other cases you'd rather deal with the hook than the quantifier. It just takes practice to know when it can be most useful. Now that 4 is a universal claim, we can do universal elimination on it and get not BA. 3 and 5 are now set up for modus tollens. That gets us not dA. In fact, 6 is set up for a universal introduction. Now there are restrictions here. The constant that we're replacing A cannot occur in the result. It doesn't, so we're fine on that restriction. And the constant we're replacing A cannot occur in any active or undischarged assumptions. The only active assumptions are 1 and 2, and A does not appear there, so we're fine. So that is a correct use of universal introduction. Now a final quantifier negation moves that hook out to the left and changes the universal in 7 to the existential in 8, and we've got 7QN, and we've shown that the goal follows from the primaries.